remain connected since the last meeting? Okay, anyways, let's get started. So first, I'd like to talk a little bit about the project. So we set some deadlines for you guys. The proposal deadline is the 28th of February. The proposal is supposed to be short. It just describes what you want to do in plain language, nothing really fancy. If you have any questions related to the project, you can ask on Slack. We're happy to answer those questions if you have any. And at the end, the reports are going to be due by the end of this semester, 15th of April. And the last week is going to be devoted to in-class presentations where you can just like entertain all of us with your beautiful presentations about the great projects that you have done. The purpose of the projects is to demonstrate a thorough understanding of some part of the theory literature. A smaller part is more appreciated than a bigger part if it comes with greater clarity. So the emphasis is that you should know what you're talking about and you should demonstrate that you know what you're talking about. Yeah, that's the goal. So if I was you, I would aim for a little review, like my favorite paper, something I always wanted to learn about, read that very carefully, and try to think about like, how would I explain this better, perhaps, than what the authors did. Many times what happens with the research papers that in hindsight, we know much more, and we can do a better job of presenting the ideas because the context changed, we know more. So that's the idea, that like you somehow demonstrate that you're familiar with, you know, the concepts, the techniques. You can relate things to other things that you have learned in class, and yeah, just produce a nice readable report.
I guess a question is, what is RL theory? Is like online regression RL theory? Is bandits RL theory? Like, do we have it?
So what are the boundaries? Well, try to stay close relatively to the class, but you know, a lot more things are going to happen in the class. If you stray too much, like if there are no actions, or like, I don't know, like, well, you can try to choose something, and then the purpose of the proposal is to propose something so that we can say no if it's too far. Something like, oh, like some people ran these simulations, how great. That's not RL theory. RL theory would come with some theorems about some RL setting. The basic RL settings are planning, batch RL, online learning. If you make it as simple as bandits, it's okay, but this class is not really about bandits, so maybe you should have some states here and there. I cannot rule out that if someone solves a big open problem in bandits, then they wouldn't get the best possible mark. They would, but it has to be really great. If you want to make it bandits, then you have to make it very, very good. I wouldn't go there. Right. Any more questions? Maybe you'll have more questions once you start thinking about it. Okay. No more questions, then let's just jump on today's topic. So the last time we got into discussing how we can use linear function approximation in planning. So you have a featurized MDP. That means that you have an MDP, and maybe it's a discounted MDP, and there is some feature function that you have access to, and someone's telling you that, hey, like all the action value functions lie in the span of the features, or like close to the span of the features. What can you do? Can you help me to come up with a good policy? And how would you do that? And so here there is this little approximation error that we allow. And it turns out that, well, the last time we looked at this, and approximate policy iteration does it under these conditions. Basically, in policy iteration, you would produce a sequence of policies. You would need to evaluate the policies here. You can use the features to help yourself. And for policy evaluation, we found that least squares with an optimal design works well if you produce targets which are a little bit biased. So you run your policy, you produce rollouts, and then compute returns along the rollouts, average those from a core set of state action pairs. And you do this a couple of times to reduce noise. The bias is small because the lengths of the horizons are big enough. With this, you can control everything, and then you can achieve a suboptimality, target suboptimality. That is something in the range of square root d times the approximation error of the features. And if you wanted to reduce this square root of the amplification factor, actually there is a 1 over 1 minus gamma squared that keep leaving out, but because we were focusing on if you wanted to just reduce the square root of d here, then you would run into trouble. There we use the Johnson-Lindenschross theorem that says that in a d-dimensional space, you can have exponentially many vectors which are near orthogonal to each other in the sense that the inner product between the vectors is, like bounded by a constant, like 1/4. So in particular today, I'm gonna say, okay, you can have e to the d vectors in a d-dimensional space all lying on a unit sphere, such that the inner product between these is at like different ones is at most 1/4. So a quarter. So that's a property of high dimensional spaces that relatively small inner products can be maintained with exponentially many vectors. Of course, if you want to drive the inner product to 0, then you only have d vectors with this property. But if you allow yourself a lag like 1/4, which is in a way a big lag, then you can already have exponentially many vectors. So, Alex, do you have any question?
I was going to say, Slack, there was a question and as to like, I think if I understood it correctly, how many arms are needed such that, I guess, phi of it, like the feature vector of the arms are orthogonal to each other, and I guess that's 2 to the d. Or
well, it depends on what level of orthogonality are we talking about, right? So in general, you can bring in a parameter, which would be this orthogonality parameter, and you would find that the number of vectors that you can get is something like, if the orthogonality parameter is 8, then like it's 2 to the d to the power of 8 or something. So as 8 goes to 0, then whatever is in exponent goes to a constant. So eventually you end up with just d, right? But if you fix a not too bad orthogonality, near orthogonality constant like 1/4, then you can have exponentially many vectors. And so the essence, I guess, like I didn't have time to answer the question, but I will answer it that too. But so remember that the situation that we are looking at was not just any bandits. Like in a bandits without any structure, obviously you have to pull each of the arms if you want to discover the optimal arm. The question is, if I add features, I guarantee that the reward function can be expressed using the features up to some approximation error. Now, how many pulls do I need? And the Jones-Only-Strauss lemma helps you to answer this question in a worst-case sense. And it will tell you that if you want an accuracy that is sub square root d of the approximation accuracy, then the number of pulls, the number of arms, is going to be exponential. So I guess it was e to the, I think, d over 8 of approximation error divided by delta squared. So this is how many vectors you can stack if you if you demand the delta accuracy and the approximation error is just this big, whatever is with it.
Just to clarify, this is for the not the setting where we want to find the optimal arm and keep pulling it, but the setting where we would demand the estimate of each arm, the L infinity norm.
No. It's for the setting where you demand that you find an arm which is delta optima.
Oh, okay.
We don't care about estimates of values. Like we just want to find good actions. But of course, in this setting, it will work in such a way that you can't find this action unless you look everywhere, because these vectors are near orthogonal. So, and by that time, you will have good value estimates as well. So the only way to, I mean, how would you use the features? Like the idea of using the features would be that you make a few measurements, and then after making a few measurements, you have good parameter estimate, and you can generalize to the actions you haven't seen. Except that if there is this approximation error, then it's really inconvenient, because now there are extrapolation errors that no algorithm can avoid. So that was the, like in a worst case sense, this is what's happening. Of course, this is just worst case. It just says that there is a bandit on which this happens with features like linear bandit. But it doesn't mean that all bandits are like this. It's easy construct features which are completely benign. Let the feature vector to be the 0 vector. You're good, right? I mean, you're good towards the, like, up to an approximation error right away, right? So the square root d shouldn't be there, because it doesn't matter what parameter vector you're multiplying 0 with, you get a 0. So the only vectors that are near realizable, epsilon realizable, are the vectors that are sticking out by an epsilon. Then all arms are equally good, so you don't even have to pull anything in this setting. So the query complexity is 0. So they are absolutely benign features that allow you to reach the approximation error right away. Of course, you can't go beyond or below the approximation error. There is for that you have to try all the actions clearly. But to reach the approximation error here, you don't have to pull any arms. So there are absolutely benign feature maps and not so benign feature maps. All what is this talking about is that if you want your algorithm to be agnostic to the choice of the feature map, which we really want because we don't want to worry about the feature maps, well, at least that would be the ideal word. Like, you don't want to worry about like one more thing. then the bad news is that, sorry, you can't do that. Like, you should better worry about the feature map. So maybe you should choose a benign feature map. But of course, if you make the feature map benign, then you're further restricting maybe the set of MDPs for which things are going to work out. So that's the dilemma. So it's I hope that this answers the question. Good. So anyway, so today I'd like to, so this kind of says that, oh, if the approximation error is positive, and if it's too large, so if this quantity is too large, this is not acceptable, then like you're done. Like, there is nothing that we can talk about if you want to be feature agnostic. So if you demand that the algorithms are feature agnostic, we better accept that somehow this is small, because otherwise no one can do anything. So if this is small, so the extreme case for that is when the approximation error is actually 0. Then what can we say? Well, we know that in this case, when you have this condition and the approximation error is 0, everything is really nice. You can still run approximate policy iteration, and then everything is nice and polynomial. That's beautiful. But of course, we only made this assumption, only allowed us to consider this case because already in this case there is a negative result. So if we want some positive result, then we would want to relax this. And the real assumptions are something like what I've shown here, that either the action value function lies in the span of the features, or the optimal value function lies in the span of the features. And then the question is, okay, like now that there are no approximation errors, that's like really like narrowing the set of problems down to a relatively small set. Can we, in this case, come up with local planners which are query or computationally efficient, meaning that their compute time is not going to scale, or query number of queries that they need to submit is not going to scale very badly with either the horizon or the dimension. And so today I wanted to talk about some newish results which came out last year, and the very last one came out this year. So these results are as follows. So if you take fixed horizon problems, so these are like MDPs where after 8 steps, the MDP stops and then new episode starts, and then the value functions are defined so that like you take into account the stage within the episode. So if you take these fixed horizon MDPs and you scale everything properly so that demanding a suboptimality of 1/2 would mean that you get something good. So maybe all the rewards are between 0 and 1. There is no discounting. So the action gap between the optimal action and suboptimal actions at the initial state is like constant. And then you 1, and then you demand that the suboptimality is 1/2. That means that this guy needs to find the optimal action. Then even if you assume that the optimal action value function lies in the span, you can show that no algorithm can get away with fewer queries than e to the some constant times the minimum of the planning horizon h and the dimension d. So if either of them, if both of them are big, then that's bad. If one of them is really small, like the horizon is 1, that's bandits. It's okay. We actually know how to do that. Like you just have to run optimal design, and you very quickly learn the parameters of Q star, because Q star is just like the immediate reward function. There is absolutely no problem. If the dimension is small, it's also fine. That's kind of a boring problem. But if the minimum of the dimension on the horizon is large, then this is very quickly getting a really hard problem. Okay, so that's one of the results. And here for this result, actually what happens is that the number of actions is going to be chosen to be exponential in the dimension. And so this is an explicit construction of a family of MDPs such that the number of actions is exponential in the dimension, such that no matter how you choose a delta, a planar that is guaranteed to return this delta optimal action at the initial state of this MDP, this finite horizon MDP, then the algorithm needs to use this exponential many queries. But you might wonder about, okay, like, is this like cheating somehow? Well, if the horizon is 1 again, like you are in a bandit problem, then having this many actions would not be a problem in terms of the query complexity. Computational complexity, yes, that's an issue, because how do you, like, what do you do? Like, it's not, like, depending on the structure of the feature map, this could be a hard problem or an easy problem if you have many actions. Because basically you need to solve argmax A, Q star, and there is only one state, so I'm not going to denote it. And so this is argmax A. And Q star is realizable, so you need to solve this. So if you quickly learn the parameter vector, and running an optimal design, you quickly learn the parameter vector. So here we assume, like in the first part, that the planner has access to the feature map, so it can calculate an optimal design. We don't care about compute cost. Calculate an optimal design, query the rewards at the calculated actions, estimate the parameter theta star. You can actually exactly compute it. Like, you set up the equations. The equations are enough, right? Like, you have independent vectors, and you set up a linear system. You just solve the linear system. You don't even need least squares in this case. There is maybe no noise. But if there is some noise, then okay, run least squares, and then that's fine. Like, you're very quickly reducing the errors. You can see that from Hovding's usual things. Anyway, so you have a very good estimate of the parameter vector with very few samples. Let's say in the noisy case, let's allow noisy rewards, because otherwise it's kind of silly. And this example is going to use noisy rewards anyways. And then you just have to solve this, and then whether you can solve this or not, that depends on how the feature vectors underlying the actions look like. So if, you know, like the action space is nice, and these are, I don't know, corners of some polytope that are described with a few faces, then this is an inner optimization problem with over a convex body described with a few constraints. Then you can solve this efficiently. If not, then well, it depends. But we're not concerned here with computation. We are just concerned with query, like how many queries you need, like how slowly are you gaining information about this MDP. If you're gaining slowly information about the MDP, that's already pretty bad. And here we see that for bandits, you would gain information very quickly, but in an MDP, you have to solve this planning problem that is 8-step long, and because of that, complications can arise. And that's the essence of this result. It shows you that indeed, lo and behold, there's a big difference with planning for 1 time step or planning for h time step, even in the presence of features which are supposed to help you like in the best possible way you can imagine, that they are exactly describing the optimal value function. Even in the presence of those features, no algorithm can do better than with an exponential complexity. So that's the first part. And I will try to explain the main underlying ideas of this construction. It would be a little bit too much to go into every little detail of this construction, but like roughly how it works, why does it work, I will try to explain. And then there is this other setting where we're making a different assumption. So it's closer to the classics, where the state value function is assumed to be linear in the span of the features. So the feature mapping in this case would be mapping states and not state action pairs to RD. And here there are two results. So one result is for the infinite horizon setting. And in the infinite horizon setting, if you allow the number of actions to scale just linearly within the dimension, then again, bad news, the query complexity is going to be exponential in the dimension up to a logarithmic factor there. It's like 2 to the d divided by d or something like that. Okay, so the infinite horizon setting with not exponentially many actions. So see that like this is a big reduction. So it's okay. It's theta, right? Like it's exactly the number of actions is going to be exactly linear, not exponential, and the query complexity is still exponential in the dimension. So that shows something about that the horizon is, yeah, like in this case, it's an infinite horizon problem. So we took h goes to infinity. So this kind of matches this result, right? But this is a different setting because here V star is in the span. And there is the other result, which is finally a not so negative result, which says that if you have the H horizon setting and you have constantly many actions, so you don't worry about the number of actions being an exponent of something. So let's say A equals 2, or a small number, not too big. Then you can find a planner whose query complexity scales as shown here. So this is the dimension, H is the horizon, data is the suboptimality that we demand from the planner, and A is number of actions. And then this B is going to be a bound on, so here B star is at S is the feature vector at S multiplied with theta star, and the 2 norm of B theta star is bounded by B. So we have some scaling with how big is this norm, but under the assumption that, I don't know, phi is bounded by 1.
Why does this term not appear in the infinite horizon case?
Because that's a lower bound and that's already exponential.
Oh, okay.
And we keep this, so the parameter vector is 1 or something, like its norm is constant. Doesn't depend on or maybe it's linearity. I think it's 1. Yeah. All right, so this is the little preview. I will see how far I get. Depends on how deep we want to go with these. Any further questions for this preview? Okay. So let's jump on this 2.1. So we want an H horizon problem. D-dimensional feature vectors. So the feature map maps state action pairs to R to the D. And actually, since we have a fixed horizon problem, here the value functions, so value function for a policy is indexed with the stage and the policy. And so for each stage, the value function of a policy gives you the total reward if you start the policy from the stage of the MVP. So here, the stage index is between 1 and capital H. So, you know, like you have these H stages. So the state space, if you wish, it's repeated. The transition structure is always the same. The policies also, they can use the stage index. We think about those as memoryless policies because, well, obviously it's going to matter how far you are from the end. Like, then you start to act differently. Because at the beginning, you can try to steer towards certain part of the state space such that here you have a good chance of collecting the big rewards. But if you are close to the end, then maybe you have no time to go up where the high rewards are. And so you wouldn't do that. Like you would just like do something else. So the number of stages left does matter. So the policies can use this. In a way, the proper way to think about this would be that, oh, the state space is expanded with the stage index, but we also want to emphasize that it's the same probability kernel that kind of applies between the stages. So let's kind of extend that description. And so then you end up with this way of thinking that, okay, the value functions have a stage index and maybe the feature maps should also have a stage index, because the assumption that we're going to make is that V star lies in the span. So if you expand that, that means that V star of H is equal to, it's Q star. So this Q star realizability. So QH star SA is equal to the inner product of the features. And the parameter vector is shared between the stages. So you can use any stage to guess what the parameter vector is. This is stage number 1, this is stage number 2, and this is stage number capital H, which is like 5 in this case. And there the process ends. So the planar would be given, you know, like some state here as not. Well, it's a shared state space everywhere. And then it has to make this many steps in the MVP. And okay, so you want to show that no planar can be very good at this problem, even under this realizability assumption. And we want to start from the construction, the Johnson-Linden-Strauss idea that somehow the features should not communicate too much, because if they do, then the planner is going to take advantage of it. So we're going to use these near orthogonal features, and we're going to use this construction that you can have roughly exponentially many actions, and you can have then V1 to VA such that all lie on the d-dimensional unit sphere, and sorry, it goes up to capital A, and the inner product between any of these two vectors is smaller than 1/4. So if we choose the number of actions to be roughly e to the d, there are just constants that I'm hiding, then it follows from the Johnson-Lindenstrauss lemma that we can find these near orthogonal vectors. So these vectors are just on the unit sphere, and they're all, they have angles between them which are very small, 1/4. And okay, so we start with this, and somehow we want to keep things simple. So maybe following the previous lower bound construction, we just want to have like tree-like structure. So this is your S0, and there are all these stages. The states are ordered, and you know, like you could ask the planner to start here, and then it would go there, and then get there, and then maybe there is some final state which is an absorbing state, and then it would do its thing over there. But like that doesn't really matter, because we always going to ask the planner to return a good action at that state at the top. Okay, and if it can't do that, then well, we exhibited a state and an MDP in which the planner needs exponentially many queries. So that's good. So we start with this tree. So in this tree, what happens is that, well, if you zoom in, here is a state. So this state has a bunch of actions connected to it. It has A actions connected to it, which is exponentially many. And we're going to make the MDP deterministic. So pretty much all of these actions are going to lead to a new state. And then from that state, you have, again, exponentially many actions that lead to new states. This is how it goes up to the end. So this is a state. Here's an action. And we are at stage H. What should be the feature? So the first attempt to choose the features is maybe that they should be just these vectors V of A, because that used to work in the other case. So why not? And then we want to argue that, well, we're going to make one of the actions optimal. So there will be an action A star, which the planner doesn't know about. And its job is only to find this action. And like this action is going to be optimal at all levels of the tree. At the beginning, maybe it gives you big reward, and so forth. And so the implication to this is that, well, what are the values? So the QH star SA It's going to be this inner product between VA and VA star. Oh, yeah, like how do you choose theta star? So theta star in this default construction is chosen to be VA star. This is the unknown. And so we know that this goes two ways. Either this is 1 if A is equal to A star, or it's in absolute value less than 1/4 if A is not equal to A star. So these values are all uniformly either small, like 1/4, or they are big, like 1. So what's the problem with this construction? Well, we didn't say what the rewards are going to be, right? But somehow at the end, okay, so we said that there's this absorbing state. So here the reward is 0. But like at the very end, you should get maybe like you have to have some rewards, because the optimal value for the optimal action is going to be 1 in the top. So the optimal action, I don't know, like I don't have green. Do I have green? Yeah, like that. That's the optimal action. That should have a value of 1. So if that has a value of 1, the others have these small values, and somehow rewards should support this 1, right? So I have to put in some reward somewhere. And well, you can try. Yeah, the problem is that maybe what a planner can do in this case is that they can just run an optimal design, and then they will want to figure out this parameter vector based on the optimal design. Well, what measurements can they do? Well, they can do measurements like, like go to some state, either here or there, and then simulate some action and see where it goes. Well, it always goes to the same place. It's deterministic, we know that. And then it can measure where it goes, and it can also measure the reward along the way. And consistency needs to hold. So it has to hold that QH star SA is the same as the immediate reward, which can be measured, and then the optimal value for the next stage. And we said that we want to somehow arrange in such a way that at the next stage, okay, so let's introduce this little notation that if I write a state and an action next to each other, that's the next state, if it stands for a state. I don't want to use a separate function or anything like that. It's just the next state. It's uniquely identified. It's the deterministic dynamics. And then A star, right? So this is the consistency equation that we need to satisfy. And okay, so if A is equal to A star, then here we have 1 on the left-hand side, and then we have a reward for this action, plus we have a 1. So here the reward has to be 0, right? Because we need to satisfy consistency. If A is not A star, then here we have a value, this QH star SA. This value is between -1/4 plus 1/4, because this is the inner product, and then we said that these inner products are like of this range. And so we have this value on the left-hand side, which is in this interval, and then on the right-hand side there is the reward, and then there is this value here, which is 1. So here we have a value in the range of -1/4 and 1/4, and on the other side you have to have a reward and the value of 1. So for the optimal actions, the reward has to be 0. And for the non-optimal actions, it has to be, I don't know, like in this interval, but it's got to be consistent, right? And then you can predict that these values are all 1, right? You don't have to measure it. It's just like, because we set up things in such a way that it's always 1. So if you want to estimate the parameter vector, then you can go into any stage, run an optimal design for that stage, and knowing that these values are 1, like without like trying to measure them, you can just know that the optimal values are 1 there. You just measure the rewards, and on the left-hand side, you have this phi h SA transpose theta star, and it's equal to the reward plus 1. So you can measure these things, you set up your equations, and after the measurements, you're done. So that's not good. We have to do something else. Like, we can't do this. This is too much. Okay? So in particular, it's not quite attractive that all these next state values, the optimal values are always 1. That's bad. Like, just shouldn't happen. That made things too predictable. This is too narrow. So then what else can we do? I mean, like, this looks like it's a good idea. Maybe what we can do is that we can scale things. So we can introduce some scaling parameters. And there are many reasons to introduce these scaling parameters.
Chava, there's a question.
Yeah. Yeah. Oh, what is the question?
So could you repeat the argument for why A is not equal to A star?
Well, there are two cases. Either A is equal to A star or A is not equal to A star. There was no argument. For all those cases when A is not equal to A star, these equations hold. A star is just one unique action. There is no chance that you're going to find it if you're randomly looking at the actions. So you don't have to think about A equals A star. And anyways, if A is equal to A star, then you will see that the reward is 0. So, and in all the other cases, there is no chance that the reward is going to be 0. There is no argument for that case. You don't need to worry about it. The chances are that...
Sorry, what I meant was like, what was the explanation for that case?
Oh, for that case, I guess like you don't... Well, for that, you just look at what happens with consistency and you see that the rewards have to be 0. So if you would see a reward that is 0, then you would be very happy, right? Because then, okay, like from here, you know that there is no chance that these inner products, okay. So what do we need to have here? This reward, this other reward to be 0. For this inner product should be just 1. But it lies in a -1/4 interval. So therefore, if you see a 0 reward, you can be sure that you found the optimal action and you're done. So the planner can just go in, run the optimal design, and if it sees a 0 reward for any of the actions that it happens to choose, then it just says, yeah, good, I'm done. If it didn't see a 0 reward, then it just solves the equations like this equation in the bottom for theta star, and again, it's done. And just have to find the linearly independent features. So this is a very bad idea to try to design your adversary MDP this way, too narrow. Okay. So what else can we do? So maybe we could introduce some scaling. Okay. And so the problem with this is slightly different. I don't know whether I want to explain all of this. This is also a bad idea. What happens is that we wanted the optimal action to beat the suboptimal actions, and that is going to constrain the sigma SAs for the suboptimal actions, and most of the actions are suboptimal in a way that reveal the identity of the optimal action. Just like, again, like you argue with this consistency arguments, like you put together everything you know, and then you will see that there will be too much information given away, but just these coefficients. So a planner can go in and then just like look at the features, and it knows that the features are constructed this way because, but the planner, we want to claim that no planner can do anything even against these MDPs, against just this narrow class of MDPs. But the only free thing is which action is the optimal. And so the planner can go in and looks at all the features. Remember that we allow the planner to look at all the features, looks at the scalings, and then from the scalings, it figures out basically the optimal action. So this is not good. So the next idea, still not giving up, is to add a bias term to the features. And then this is what's going to work. So the features are going to be, I think, some constant, and then some scaling of these GL vectors, and concatenate the whole thing. So this now lives in RD plus 1. Fine. So again, thinking about consistency and how to avoid a planner, just running an optimal design and gaining too much information. One attempt, one possibility is to set the rewards to be 0, okay, everywhere. So rewards here, 0. Rewards here are 0. All the rewards are 0. Except at the very end. So here, random rewards. So if everything was deterministic in an MDP, then it turns out that there is an algorithm for this case, which would be able to figure out a good action with polynomial many queries. So the deterministic MDP case is very special. You can't keep everything deterministic. And then you might wonder about, okay, so either I can make the transition structure stochastic or the reward stochastic. Transition structure stochastic, that seems too much hassle. Why don't we just keep the tree structure? So let's make the rewards random, but we don't want to reveal too much information with the rewards. So we want to take advantage of the randomness of the rewards. How can we do that? Like how to take advantage of the randomness of the rewards. And here the idea is going to be that we are going to scale up the features for the first stage. So the first stage here, phi 1, the magnitude of the features is going to be 2 to the h. Don't take 2 seriously. It's just exponential in age. And at stage age, the magnitude is 1. And theta star, the magnitude of theta star, to keep everything under control, is going to be 2 to the minus h. The point is that in the bottom, the values, the range of the values, is 2 to the minus h. And so if you run an optimal design, so there are no rewards anywhere except at the very bottom. If you run an optimal design at the very bottom, you see these features of magnitude 1. You need to estimate the parameter vector of this small magnitude. So let's say you use, like n observations. Then you get this 1 over root n errors, right? But then here, these features, they are 2 to the h bigger. So your errors are going to be blown up by a factor of 2 to the h at the first stage. So you get an error of 2 to the h divided by root n, or something like that. Actually, 2 to the h goes under the root, but it doesn't matter. And so that's hopeful for the adversarial planning, because now the planner cannot do much, right? Like it cannot run optimal design and just be clever about estimating the parameters, because there is an order of like exponential order of magnitude of difference between the values at the root versus at the bottom. At the bottom, the values are tiny, tiny. And so at the end of the day, the way you're going to implement this is that these rewards are going to be random, Bernoulli, with these small parameters, like parameters of the size of 2 to the minus h. So imagine that someone runs the optimal design and then wants to estimate the rewards. Well, the mean value of the rewards is 2 to the minus h. How many pools do you need of a Bernoulli random variable of a mean of 2 to the minus h to know that, okay, this value is actually 2 to the minus h or 2 to the minus h over 2? That's going to be a big difference at the root. Well, you have to put it 2 to the h times. That's the lower bound that we want to show. So that's how it works, right? So to get precise enough estimates at the bottom, the planner would need to do a lot of simulations there. Okay, so that's kind of the plan. So all the rewards are 0. At the bottom, we have these tiny little random rewards. And then the top, we want big. So at the top, V1 star is about the value of 1. How does that happen if we don't have any rewards in between? Well, it cannot happen, because V1 star is the sum of the rewards underneath it up to the end. It's 1, and the only rewards was 2 to the minus h. Doesn't add up. It's not consistent. So now we have to add something else. And the something else that we add is kind of like an exit lane. So we keep the previous design. So there is this phi1 that's like of the size of 2 to the h. The optimal value here is supposed to be 1. There's this phi h that's of the size of 1. The theta star is of the size of 2 to the minus h. Okay, imagine there is a norm everywhere. And so the values here in the bottom are of the size of 2 to the minus h. See all these layers, and then this absorbing business. We're going to have this exit lane. So The exit lane starts at stage 2. And the way it works is that if you have your optimal action, A star, then it bumps you out of the tree. So A star always lives to there. It results in a deterministic reward such that consistency holds. Here the values, the values here over the exit lane are going to be all 0. So this has the same number of stages. And at the end, it goes to the observing state. But there are no rewards there. The feature vectors are all 0 there. Everything is boring. So once you get on the exit lane, nothing happens. Okay? Why do we do this? It's because we have to support that the value here is 1. So we're going to say, oh, this value is 1. Big deal. We have exponentially many actions here at the root. One of them is A star, good luck planner. If you're not hitting that special action, you will never find the optimal reward. I mean, like you don't find a different, like all the other rewards are 0. So if you're randomly choosing actions there, you just see zeros until you choose all the actions. Then you still the 1. So it's like needle in a haystack. It's like on steroids, like everywhere. Right? Like you have exponentially many actions here, there, like number of states really blowing up. Of course, the feature dimension is get fixed, but Jones-only really does have a lot. Okay, so that's one thing. The other little addition. Oh, so what happens to the optimal action at any other stage? Well, it's the same story. It always quits. And it always gives you the right amount of reward that depends. Since the features are scaled, these rewards are going to be scaled. So this reward is going to be at stage age, is going to be roughly of 2 to the minus age size. But it is the same story, just like to keep consistency. And there is one more little thing, which is that if you're coming down in this tree and you chose some action here, I don't know, a knot. And then later on in the tree, you choose the same action, a knot. Then that also brings you to the exit lane. So if you repeat the same action in a sequence, so we are eliminating from the tree all the sequences with repeat actions. If ever a repeat would happen, the first time the repeat happens, the result of that is not to stay in a tree, but to go to the exit line and get a reward of 0. So that's like a big punishment. So just if anyone wants to do repeat actions, they are welcome to do. It leads to nowhere. It leads to the exit line where there are no rewards. And this is required to help us with the consistency proof. Probably one can maintain consistency even without this, but it's a little bit easier. And then, okay, what else remains to be done? This is the construction. Again, here there was Bernoulli 2 to the minus h rewards. Here the rewards are all 0. And yeah, that's the construction. So the question is, okay, can we somehow come up with a constant such that consistency holds? So we said that the features are going to be such that there is this constant, and then there is this scaling factor which scales VA, and theta star is going to be also some constant times VA star. Well, the constant, we already know that. Well, we want to choose it something exponentially small. And then the question is whether we can choose these in an appropriate fashion such that consistency holds, so that we can support a Q star. So for any state and action that appears here, we need to show that Q star of H SA is the same as phi H SA transposed theta star. So this puts a bunch of constraints on these free variables here, because this has to hold for every state action pair. So the exit lane is a no-brainer, that the features are 0, so optimal values are 0, everything is fine. Within the tree, there are a number of cases. You are at a state and you're choosing the optimal action that will go to the exit lane, or you are staying within the tree by choosing some other action, or you choose a repeat action. Like, there are all these cases that you need to consider. In the interest of time, I'm not going to go through like how you can argue of how you should be setting up these constants, but it happens that you can set them up. So that there exist CH and C, SA and C such that this consistency holds. And you prove this based on looking at what the Bellman equation would do, knowing that you wanted to have A star to be the optimal action at every state. So you just use this, and then it's just like a straightforward recursion that you have to set up to define all these constants, and you unravel the recursion, and like you find all the constants that you wanted. It's not it's just calculation. It would take an hour to go through it. It's just detailed calculations. So once this is done, then we see that, okay, this is going to fly, right? Because what can a planner do? But if the planner is not using too many queries, then it's going to run into trouble, because it's not going to randomly just like hit. If it's not using too many queries, it's not going to hit A star. If it's not hitting A star, then it knows nothing. If it was spending all its effort in the bottom, then it learns very little, because this Bernoullis give you no information. If it queries everywhere it has, it gets zeros. Like, everything looks symmetric. So that is the symmetry that you exploit in the formal rigorous proof at the end, to show that if there is a planner, it spends its effort somewhere, you can always find a value for A star where it was not looking. So in particular, you let the planner run in a benign version, in a gray version of this MDP, where there is no A star. Like, everything else is the same, except that like you get rid of the A star. So the rewards are defined to be 0 everywhere, these Bernoulli rewards, and then it doesn't matter which action it tries at what node. It just like, if it's a repeat action, it goes to the exit line. If it's not a repeat action, it just stays in a tree, gives you a 0 reward. In the bottom, it gives you some Bernoulli reward, and that's it. And then you measure in this benign MDP what the planner does, where does it spend, like what actions it sees. And if the planner doesn't spend 2 to the H queries, then it cannot choose all the actions to do the A, like the smallest of the two, right? Like that's where the smallest of the two comes in. If it doesn't choose that many queries, then it cannot choose all the action. You choose the action that it was chosen with the least frequency, and with large probability, you will find an action that whose chance of being tried is small. And then you argue that, okay, on this MDP, the planner cannot do well. Okay. Yeah, that's kind of the gist of it. Okay, so in the remaining 5 minutes, let me explain the two other things I wanted to do. No, that's not possible. Okay.
There was a question.
I can explain. Okay, so if there is a question, that's also good. Or I can explain just like what happens in the infinite horizon setting, because that's easy. But I'm happy to answer the question. What was the question?
Fatima asked, can you explain again why we want to hit the exit link when we repeat the action?
It's easier to maintain consistency of so you want to maintain this this equation, this star, this. It's gonna be easier to satisfy. You just like if you have these repeat actions, then with the recursive definition of the sigma as A, you would have a little trouble. So it's better to avoid that. You have to look at the details of the calculation to understand why that is the case. It's not that just comes from doing things.
Sorry, just can you also repeat what was the sigma SA supposed to repeat?
It's just a real number. It's gonna be a positive real number. It's gonna be between 1/4 and 1. And we are setting up these equations and then solving for these numbers, including C, in such a way that these equations hold. So that would be kind of a recursive reasoning. Yeah, just a case-based analysis, right? Oh, there is a case when A is optimal. Oh, there is a case when A is not optimal. What happens in this case? What happens in this? And then from those follow constraints on how these constants, CA, sigma S, A, and C have to behave. And eventually you show that, well, I can choose this in such a way that all the constraints that I have can be satisfied. That's it. Make sense?
Thanks.
Good. All right. So then maybe I can explain this infinite horizon business. I'm always overestimating how far I can get. So the infinite horizon case, it's just nice. You start with the d-dimensional hypercube. I just show you an example in 3 dimensions, but this is really, actually you add a 0 as well. So this is going to be the state space. So that's 0. And the actions are going to be to move to a neighboring state. A neighboring state is a state which only differs in one coordinate. Everything is deterministic. There is an optimal corner that you want to get to, and we're going to switch to costs. The cost of every move is 1, except if you are at this state, you also add actions that can stay put. So there are the actions that can that can change one coordinate up or down. And there is also an action that can stay in put. And if you're staying in put at any state other than S star, then you suffer a cost of 1. You move along an edge, you suffer a cost of 1. And here, if you, so these are costs. Here, if you're staying put, then you suffer a cost of 0. So this is the complicated way of describing that you're on this grid. And you can navigate by going to neighboring sites. And you want to get to S star in the fewest number of steps, because we are minimizing cost here. It's the same thing as maximizing reward, right? Just negative reward. Negative cost, that's reward. And the beauty of this is that if you take a state, so a state is -1, 0, 1 to the power of t. So each coordinate is -1, 0, or 1. Then the cost to get to S star is going to be what? I forgot. It's like the inner product between S and S star. I don't know, like right. Actually negative, and do we need to subtract from D or something? Yeah. So that's the number of. So if you start anywhere, you look at a coordinate, and if it differs from the coordinate of S star, then you can change it towards the S star coordinate. And yeah. So you can write this if you define the feature vector to be just 1 and S, then I think the values, the optimal values, are going to be just phi S, I think D minus S star. Right. So if S is equal to S star, then you get the inner product is going to be D, right? Otherwise, you're counting how many differences you have. And so if S is equal to S star, then like you get a 0 cost, and otherwise you get the cost. It's the number of steps to go. So this navigation on the hypercube is linear with these features and with this parameter. And it's a hopeless problem. If you don't get to S star, like the MDPs, which are the same, except the identity of S star is different between the MDPs, you can only distinguish between them if you know what S star is. Because all these MDPs look the same in terms of the dynamics of the rewards, except that S star, that single state. And there are S star has to be in the corner for this to work. For some reason, my pen doesn't work anymore. So S star has to be in a corner. There are 2 to the D corners. Okay. So if a planar uses cost significantly less than 2 to the D, they have no chance of figuring out where S star is. Therefore, they're going to be randomly wandering about. And so this is where the exponential dependence on the dimension comes from. It's quite curious. Very nice, right? Again, a needle in a haystack, right? So every time you would need to prove this, you would go back to homework zero's little problem of like, there is this array, there is a 1 in it, like, oh, all algorithms have to look at all the entries in order to be able to tell where the 1 was in the array. All of these proofs are the same of this quality. These MDPs, they're all linear, described by the optimal value function, you know, this parameter. But the local information that you can get from looking at transition dynamics and rewards in these MDPs doesn't reveal anything about where you have to go. The goal is somewhere, you don't know where. So very clear that for infinite horizon settings, there is some big problem. It's the features do not have much. We don't know whether the same holds if you have a constant number of actions. So maybe if you have a constant number of actions, then infinite horizon is not a big deal. We don't know that yet. For the finite horizon setting, we know it for sure that query complexity wise, if you have constant number of actions, then under this V star realizability condition, the query complexity is nice polynomial in the relevant quantities. That's going to remain for next Tuesday. Right?
How important is this result? Because this seems like a very specific MDP construction. Like, do these arise a lot?
It rules out, no, I mean, like, why are we talking about this, right? So why on the earth are we talking about these very specific cases? It's because people are saying things, oh, I just want an algorithm that works under this ideal setting. For example, V star realizability. Like, can we design a clever algorithm that takes advantage of this? That is the question. And this very sharply answers with a big no, this question. So we are always wondering about, are there better algorithms than what we have discovered so far? The only way to answer this question is to really ask, like, under these ideal conditions, is there anything better than what we have been doing? So in this case, what we say is that, well, these conditions are not that ideal in this setting. Like, it is a big hurdle. Like, if you want to claim that your algorithm works in a reasonable way, well, this setting is not such a setting where you could make any such claims for any algorithm, not any particular algorithm. It is like a very, very big warning sign that, hey guys, you're thinking about that features function approximation is going to be a big help is not true, because it doesn't have any algorithm. So when is function approximation useful? Well, if you were hoping that it's going to be useful already when you are assuming only that V star is realizable, you're wrong in the infinite horizon setting. So you need to be more modest. Like it has like these every negative result tells us that we try to do something too hard, and we're not going to succeed. So it's time to give up on that. Time to consider something more constrained. What's funny here is that we saw that this is already very constrained because you have exact realizability. You have D unknowns. D is a small number. And like how on the earth, like you want to just to know these D numbers. If you know the D numbers, you would be done. But the information is presented to you about the MDP in a way with this local information, with generative models, whatnot, that it's just like impossible to get these D numbers without trying everything, without an exponential cost. So either we have to keep D very small, or we can consider the other settings which made much stronger assumptions about function approximation, like the approximate policy iteration setting, where we assume that all Q functions lie close to the span or lie in a span. In that setting, yes, we have efficient algorithms. So it's like going through all these cases, like if you find in this case, like we didn't know that, like you're gonna find this, right? If you found that, oh, there is a clever algorithm, this is how it works, then okay, we would say that, okay, yeah, that's good, like that's good to know. Is it an algorithm that we know and love? No, that's really interesting. Yes, it is. Okay, fine. Business as usual, right? So for the API result for that setting, we found that, okay, like it's kind of fabricated. The setting is fabricated to make API work. Yes, API works. Approximate policy iteration works. If you consider these less fabricated settings, then we suddenly find these hardness results that tell us that, well, even this problem is too hard. And you must give up on problems that are too hard. Like you can't claim that you work on this problem because like it will never, I mean, like it's the best for applying to grants as long as the people who are looking at your grant application do not know about the hardness result, because then it will take forever to come up with an algorithm that works for this setting because it will never work. The next time we're gonna find some setting where the answer is going to be positive, right? Like it could have gotten that way to here before this example. So the example is super important. I claim that however studied these examples are, their importance is not that you will see them in practice, but they stop you from thinking about problems that are just straight impossible. And then they keep you grounded as well. Like if someone starts to tell you that, oh, I have this super algorithm that solves all these problems, then okay, like, yeah, like, can you clarify a little bit by what you mean by that? Does it at least work in this setting? Well, for example, in this setting, well, in this setting, nothing works, so it cannot work in this setting, right? So, I don't know. I hope that it's clear that. So these negative examples, like in computer science, you're full of these lower bounds, and then sometimes people somehow question of like, what is the value of like a worst case lower bound? Well, the value of the worst case lower bound is that it keeps you grounded. It tells you that you have to look deeper, and like if you really want to claim that your algorithm is fast, then you can't be claiming for this setting. Before you knew that there was this example, you couldn't tell whether that's possible or not. So it's like flags, like don't go here, don't go there, mines, boom, this is bad, stay away. And then finally, maybe you will have a little island where you can happily design your algorithms. And it becomes interesting if the algorithm that you need to come up with is a little bit different than what everyone was trying before. And the next time we will see that, the next lecture, that we have one such case. So at least the algorithm is a little bit different than the standard algorithms that we looked at before. Value iteration, policy iteration. It's not of that type. What is it? And we don't know. Yeah, for that setting, maybe value iteration, policy iteration doesn't work. Most likely it won't work. Most likely you can construct a lower bound that shows that for that setting, those algorithms are bad. We haven't done it yet, but that's a good project. All right.
Shab, I had, so maybe this is like a little bit philosophical, but in the finite horizon problem, like even if somebody hands you the Q star, like a witness of this, and even then it's computationally like hard to actually like implement the policy, right? And we are not really considering computational hardness, but is there any deeper meaning to that? Like, is there something weird about this problem where like even if somebody gave you the answer and talked about computational complexity, we don't know of a way of like actually finding an optimal policy?
I mean, so there is this difference between information complexity and computation complexity of a problem, right? So if you have this kind of black box optimization problems, then we can think about like how long does it take to extract information from the black box so that we sufficiently know it. And so the deeper meaning is that we know for that setting that that the computation, that the information complexity is exponential already. Not talking about computation complexity. It's a little bit weird though, right? Because like this, because the number of actions is exponential, it doesn't leave any room for the possibility that the query complexity how is it, like query complexity always trumps computation complexity. So the computation complexity is always bigger than the query complexity, of course, but if you started with exponentially many actions, then you already know that the computation complexity is going to be exponential. So there is nothing left to be proven about the computational complexity. And the only interesting question remains whether the query complexity is big. But maybe it would have been more like it would be more interesting to have an exponential lower bound for the query or information complexity for the case when the computation complexity has a chance of being bounded. By the way, so let me think a little bit. So I'm thinking about that if you replace the Johnson-Linear-Strauss lemma with some more regular construction, where the computational problem can be solved because you just have a nice structure for the features, then potentially this is computationally feasible. Because the only trouble we have is if theta star is given, is that we need to solve a linear optimization problem over the action space. And so if the features, these vectors are carefully selected, then maybe you can do that in an efficient way with a dual representation or whatnot. And so it may be possible. So that's also an open question, whether this construction can be defined in such a way that there's a, like if theta star was known, the computation complexity would be nice.
Yeah, and that makes sense because otherwise you could claim to have a planner that only works in MDPs where there is a computationally feasible policy or something, right? So a policy that takes some small amount of information and then
Right.
rolls it up. Right.
Yeah.
I guess there is one simple thing. Like you could say that if you had a maximizing oracle that tells you the optimal action for a Q star, and then it doesn't seem like that oracle would help. So that would create like an immediate gap because that oracle would help you execute the policy, but it doesn't seem like it would help
Sure.
you.
Well, I mean, like that's obvious, right? Yeah, exactly. So, but it doesn't quite resolve the problem because where do you get that oracle? It just like makes the difference or the statement a little bit cleaner. And people, yeah, of course, do this a lot of times that you assume some oracle and then assuming that you have the oracle, like, can you do this? Can you do that? Yeah, here you could phrase the first result as saying that if you assume that there is an optimization oracle, then still you cannot have an efficient planner, even in the presence of an efficient optimization oracle. It would be better to have an unconditional statement that doesn't rely on that the oracle is efficient. But I think we're pretty close to that. Maybe some more thinking will give that answer too. That's another good.
Unless there is some fundamental reason that a Johnson-Linden-Strauss type thing cannot exist for a computationally nice set of vectors, right? And that would be interesting if that was the case.
I don't think that that's the case.
Yeah.
Okay.